Today, we are mastering the fundamental representations of complex numbers and the operations performed within these forms. This topic is a cornerstone of the higher-level analysis and approaches syllabus. You will learn how to transition between Cartesian, polar, and Euler forms, and how to perform operations efficiently. In the IB examinations, these concepts appear frequently in Paper 1 for non-calculator algebraic manipulation, and in Paper 2 for geometric interpretations and complex roots. Understanding which form to use can save you significant time under exam conditions. A complex number z can be expressed in three primary forms. Each form serves a specific purpose. The Cartesian form, a plus bi, is your algebraic bread and butter. A is the real part, and b is the imaginary part. We use this primarily for addition and subtraction. The modulus argument, or polar form, introduces r, the modulus, which is the distance from the origin, and theta, the argument, which is the angle measured from the positive real axis. Finally, the Euler form, re to the power of I theta, is arguably the most elegant. It is derived from Euler's formula, e to the I theta equals cosine theta plus I sine theta. This form is a powerhouse for multiplication, division, and finding powers. Notice on the Argand diagram how these forms relate. The modulus r is the hypotenuse of a right-angled triangle, and theta is the angle of elevation. To convert from Cartesian to Euler form, we need two values, the modulus, r, and the argument, theta. The modulus is found using the Pythagorean theorem, representing the distance from the origin to the point in the complex plane. The argument is found using the inverse tangent of the imaginary part over the real part. However, you must be careful. The standard arctan function only returns values between negative pi over 2 and pi over 2. For IB, we use the principal argument restricted between negative pi and pi. You must always sketch the point to ensure your angle is in the correct quadrant. Let's convert z equals negative 1 plus I root 3 to Euler form. First, let's calculate the modulus. First, r equals the square root of negative 1 squared plus root 3 squared, which simplifies to the square root of 4, or 2. Next, look at the coordinates. Since a is negative and b is positive, we are in the second quadrant. The reference angle for root 3 over 1 is pi over 3. To get into the second quadrant, we calculate pi minus pi over 3, giving us 2 pi over 3. Our final Euler form is 2e to the power of I, 2 pi over 3. First, let's look at addition and subtraction. For adding or subtracting complex numbers, always stick to the Cartesian form. It is purely algebraic and intuitive. You simply combine the real parts and the imaginary parts independently. Geometrically, this is identical to vector addition. If you represent two complex numbers as vectors from the origin, their sum is the vector that completes the parallelogram. While you can multiply in Cartesian form using expansion, it is much more efficient to use Euler form for multiplication and division. When multiplying, you multiply the moduli and add the arguments. Geometrically, this results in a dilation by factor r2 and a counterclockwise rotation by the angle theta 2. When dividing, you divide the moduli and subtract the arguments. This corresponds to a dilation by 1 over r2 and a clockwise rotation. Let's find the product and quotient of these two numbers. For the product, multiply the moduli to get 2 root 2 and add the angles to get 3 pi over 4. For division, 2 divided by root 2 simplifies to root 2. Subtracting the angles gives negative pi over 4. This is in the required range for a principal argument. When we raise a complex number to a power, we use de Moivre's theorem. This is simply an extension of our multiplication rule. We raise the modulus to the power of n and multiply the argument by n. This makes calculating high powers, like z to the power of 10, incredibly fast compared to expanding brackets in Cartesian form. The complex conjugate is another vital tool, especially for dividing in Cartesian form or finding roots of polynomials. If z is re to the I theta, its conjugate, z star is re to the power of negative I theta. Let's find the conjugate of z equals 3 cis pi over 6. In Euler form, we simply change the sign of the argument. In polar form, this looks like changing the plus to a minus between the terms, because cosine of negative theta is cosine theta, but sine of negative theta is negative sine theta. Geometrically, taking the conjugate is a reflection across the horizontal real axis. The distance from the origin remains the same, but the angle is mirrored. Let z1 equal root 3 plus I and z2 equal 1 minus I. A. Express z1 and z2 in Euler form. B. Hence, find z1 divided by z2 in the form r e to the I theta. This is a classic paper 1 style question where you must demonstrate fluency between forms. For part A, let's look at z1. The modulus r1 is the square root of root 3 squared plus 1 squared, which equals 2. Since both parts are positive, it is in the first quadrant, so theta 1 is arctan of 1 over root 3, which is pi over 6. So z1 equals 2e to the I pi over 6. Now for z2. The modulus r2 is the square root of 1 squared plus negative 1 squared, which is root 2. The point 1, negative 1, is in the fourth quadrant. The principal argument must be between negative pi and pi, so theta 2 is negative pi over 4. Thus, z2 equals root 2e to the minus I pi over 4. For part B, we use the division rule for Euler form. We divide the moduli and subtract the arguments. Substituting our values, z1 divided by z2 equals 2 over root 2, e to the I times pi over 6 minus negative pi over 4. 2 divided by root 2 is root 2. For the exponent, we find a common denominator of 12. 2 pi over 12 plus 3 pi over 12 gives us 5 pi over 12. The final answer is z1 over z2 equals root 2 e to the I 5 pi over 12. This approach is much faster than multiplying the top and bottom by the conjugate in Cartesian form. The most frequent error is simply calculating the inverse tangent and moving on. For example, if both a and b are negative, the point is in the third quadrant, but your calculator or the basic arctan formula will give you a first quadrant angle. Always sketch an Argand diagram to verify the position. Second, incorrect range for the principal argument. IB examiners expect the principal argument, theta, to be within the range. Negative pi is less than theta, which is less than or equal to pi. If you find an answer like 3 pi over 2, you must subtract 2 pi to get negative pi over half. Third, mixing forms during operations. Students often try to add complex numbers while they are still in Euler form. This leads to messy algebra. Convert to Cartesian for addition and subtraction, and use Euler for multiplication, division, and powers. Tip 1. Look for exact values. In paper 1, you will almost always be working with the special angles, pi over 6, pi over 4, and pi over 3. If your calculation results in a strange angle, go back and check your modulus and tangent ratio. Tip 2. Use the hence cue. If an IB question says hence, you must use your previous answer. If you've just converted numbers to Euler form, part B will be significantly easier if you stay in Euler form rather than switching back to Cartesian. Tip 3. Show your sketch. Even if the question doesn't ask for it, sketching your complex number on an Argand diagram can earn you method marks if you make a calculation error in your argument. It is time for some homework to consolidate what you have learned. Easy. Convert z equals 1 plus I to Euler form. Medium. Given z equals 2e to the I pi over 3, find z squared in Cartesian form. Hard. Let z equals negative root 3 minus I. Find z to the power of 6 using de Moivre's theorem. Please pause the video now and attempt these questions before we move on to the solutions. Here are the homework solutions. For the easy question, we first find the modulus. R equals the square root of 1 squared plus 1 squared, which is root 2. Next, the argument, Theta equals arctan of 1 over 1, which is pi over 4. So, z equals root 2e to the I pi over 4. For the medium question, z squared equals 2 squared times e to the I2 times pi over 3, which is 4e to the I2 pi over 3. To get to Cartesian form, we use the polar expansion 4 times cosine 2 pi over 3 plus I sine 2 pi over 3. This simplifies to 4 times negative 1/2 plus I root 3 over 2, giving negative 2 plus 2I root 3. For the hard question, we first convert z to Euler form. R is the square root of negative root 3 squared plus negative 1 squared, which equals 2. The point is in the third quadrant, so theta is negative pi plus arctan of 1 over root 3, which is negative 5 pi over 6. Now apply de Moivre's theorem. Z to the 6 is 2 to the 6 times e to the I6 times negative 5 pi over 6, resulting in 64e to the minus I5 pi. Since negative 5 pi is equivalent to negative pi, we get 64e to the negative I pi. Expanding this gives 64 times negative 1 plus 0, which is negative 64. First, master the 3 forms of complex numbers. Understand the strengths of each. Cartesian for addition and subtraction, while Euler and polar are best for multiplication, division, and powers. Second, prioritize modulus and argument geometry. Always visualize complex numbers on an Argand diagram. The modulus represents the distance from the origin, and the argument is the angle from the positive real axis. Third, remember the quadrant rule. When converting to Euler form, always check the signs of the real and imaginary parts. Ensure your argument is in the correct quadrant and within the principal range of negative pi to pi. Finally, focus on operations efficiency. Use de Moivre's theorem for powers and the properties of exponents for multiplication and division to solve complex algebraic problems quickly and accurately.